It's a dual resonant circuit, half bridge down there, a couple of MOSFET switches, small heatsink, driving circuitry. I've got a couple DC leads here coming off this supply. So this supply right here is the whole powerhouse. So that's driving the logic. It's going to be about 18, 20 volts or so. Then on the side there, I'm coming out with a jack powering this little tiny inverter sitting here. That's going into this little variac, and that variac's going out into the supply. So I've got a battery powered driven setup, and I'm varying the voltage, so hopefully I'm not going to kill anything. Typically what happens is if it starts chugging too hard, that inverter is just going to crap out, reset. Likewise, I've got OCD on here, so I've actually set the OCD back to where it'll trigger well before what it would when I was typically running a separate coil. I've got it at 75 VAC right there. So I'm going to cut the on time down a whole bunch and just leave it running. And you can hear it running. So if I cut off the output, just go like that, you can hear it running. It actually interferes with the camera a little bit. So I'm going to let that run. I'm going to take my little loop here and hold it up. So we pick up this ringing that actually occurs. If I can hold this right. So this is ringing, and it says about 130 kilohertz. All right, so this is not actually ringing in what it looked like it was before. But so this is just the L1 tank part. I'm just going to leave it like that just because I'm just using that capacitor. This coil gives me about that frequency. 130 is not bad. I can deal with that. And man, is that thing hot already. So we got this thing hot as crap. It's running off this little dead battery. Those don't even feel any heat at all. It's just a little tiny heat sink. Do have a fan on it. Those should be fine. But this thing right here is so hot, I can just touch it and feel how hot it is. I can't pull it out and grab it and hold it because that's how hot it got. So again, let's just pretend instead of that we've got a coil in there. So one dilemma I'm thinking is you don't typically see the primary on the inside of a Tesla coil. What doesn't make a whole lot of sense. In some situations it could work, but I don't think that would be the most wise. So throwing this secondary over top here is probably not going to be the best way to go. Although, you know, it might work all right for a Tesla coil given how you want the geometry and the coupling coefficient. What I'm going to try to do is go with a smaller coil that's going to go on the inside. I'm going to try to achieve a fairly loose coupling. This is a resonant transformer now. Going to be a resonant transformer. This is not regular transformer action where you could do like what maybe like Don Smith says and just calculate your turn ratio. That's not how it works. You have a Q factor, you've got a coupling coefficient, and all of these things go together to give you your output voltage. So your coupling coefficient is going to give you a particular Q factor because basically the higher the coupling, the more, let's just say, the more damped your resonance is going to be, the power transfer. The looser the coupling, the more free of a resonator you have. It's going to have a higher Q. And that's just how this goes. So the higher the Q, the more your amplification. So that's just resonant transformer action. Really, the limiting factor here, what's keeping things from exploding and this capacitor ringing too high of a voltage, is the on time that is being limited here. So this is modulated by an on time. It's not always running. Kept a very small window of on time to make sure that ringing builds up but doesn't exceed too high. Then you've got all this primary current. Primary current needs to go somewhere in this tank. Typically you want it to go through the secondary in the form of streamers, which ends up being a resistive load. I can still illustrate a load though. So now that it's going, I'm going to take a random inductor that I've just wound from a ZVS driver. This is just this guy right here. Still got the capacitor on it. I'm going to hold my fingers on the output, hopefully not get shocked because it's high enough frequency. Alright, so I'm going to try to hold this loop up close. And I can feel a little bit of buzzing in my fingers. But clearly the voltage is high enough to like that. I just changed to a very small battery. Fresh one, but not really loading it down, drawing very little power to do this conversion here. And I've actually still got that load in the middle, that steel core. All right, so this is just a random coil. So what this is also showing is, I've got this steel core still inside and it's hot as crap. But again, this is showing why this type of core is not effective for high frequency. One might wonder, well, you got the steel core in there, then maybe it's just working way better. because you've actually got a core. I'm gonna let it cool down and take it out and then run it again. But in actuality, what's happening is it's heating up and becoming a load because it's made out of steel. That particular transformer is just not going to work at this high of a frequency. There's too many losses inside the core itself. So actually, now that I think about it, the frequency I was reading in here before, I had the actual freaking core in there. I really wasn't thinking about it. So now let me take the core back out and read the frequency again. All right, so I just didn't really want to load it or run it without a load, but I could just turn the voltage down real low, as well as the on time. So now this makes more sense, the resonance. All right, so here we go. This is the same resonance that I was running at before, about 160 kilohertz. So that makes sense. And I wasn't even thinking about that, but putting the load in there had dropped the frequency. So that's how that works. So the same thing applies if, let's say, you know, I load the primary LC down with this right here. The frequency is going to drop. So let's say I do wind a second resonator, put it on the inside, whatever I come up with. If that second resonator ends up being driven at resonance, then technically speaking, you should have the most power throughput. You know, you basically want to turn this inductive element into more of just a straight resistor. You know, it's going to act like a DC circuit at resonance, more or less. You have less losses. As far as impedance matching and all that, it's like at perfect resonance. It seems like all these problems go away. Once you start adding loads, dynamically changing the load around, at that point it's like, well, now you need to really start thinking about impedance matching. All right, so since I've already got the coil wound, I'll just try it. So I've put it around the L1, and I've just currently got some clip leads across both legs on the output of L2, going over to this 60 watt bulb right here. I got it at like, what's that, like 27 volts. 27 VAC, something like that. Cut this on. So when I get it running, that's with the duty cycle all the way up. So I can cut it up and down. Can change the interrupter frequency like that. Cut it up even more. So that's how I really start getting it to draw power. The only thing is I don't have an ammeter on it to actually show what the current into the inverter is. But that's not bad, right? So this is just an untuned coil. And I'm just varying the on time up and down. This is a example of a much more efficient logic approach to what I was doing before. By trying to bam with a spark gap, because at this point I'm efficiently ringing the L1. Before I was ringing it by just discharging it, letting it ring down. Now I'm building up this ringing through a rising resonance, which is transferring, you know, more power over here. Have it again. Let me tune it a little bit. So with the way that is, I need the pretty low coupling like this right here, right? So if I got that up all the way, that's not full brightness or anything like that. I'll cut the OCD back. So all the way down there is the point where the OCD trips in. The voltage is very low on here. So now let me cut the on time back and the BPS real low. All right. So cutting the voltage up. Still under like 75 on time. So that's starting to get about full bright right there. And cut the OCD back. Yeah, it's still bridge seems totally fine with that. Again, it's just random coil. Wow, this is probably way more efficient than what I was doing before. What I wouldn't want to do is go ahead and take this output and unplug it. If I was to unscrew that bulb and remove that load off the secondary right there, that primary is probably going to crap out. The OCD is hopefully going to save me, but that would be a condition that would probably end up killing the primary circuit, especially if I had enough power pumping into that LC right there. Needs a load on it. That's the only thing. That's why I like messing with the spark gaps. I'm just assuming this is not magically finding some resonance or very close to it. Maybe it is, it's possible, but I'm just assuming that it's not. Let's just cut it on and see what it does, what type of voltage output I'm actually getting on the L2. Yep, there it goes. So I need about right there to get it feeding back, which is just barely anything, you know. So I'm gonna get it like that and cut it back. I'm gonna cut the on time up some more. It's a little brighter. It's actually starting to burn out that terminal right there. Let me cut it up some more. And I'm gonna play with the frequency. I'm gonna cut the BPS up a little bit. The on time. So you can see that's got to be a pretty high voltage because it's starting to burn out. All right, so now the 90 watt halogen bulb test, right? I'm gonna set my voltage at just a little under 50 VAC on here, just to be safe. I'm gonna run the same halogen pretty much the same way I did before, except before I had the spark gap, but now using the much more efficient drive. And just got a little drill battery down here. It's kind of hard to see, but just a small drill battery sitting at about 18.7, which, you know, typically if I try to drive something like that at anywhere close to full brightness on other circuits, it's really going to start pulling a good amount, and that battery might have a hard time doing it. And I've got the on time down. Cut that up. I'm just cutting it up a little bit. Nothing's really struggling. Battery does drop, you know, because it is having to convert up to 120 VAC and drive everything else, and convert up again in the LC, and more or less convert over this L2 here. So I can crank that up pretty high. All right. So this is about what I was looking at all the way up with the spark gap setup. But I was pushing more power. So cut the BPS up a little bit. Oh, really starts driving it harder. Hey, the inverter finally starts kicking out there because of low voltage. Plus it's a crap inverter. But I mean, I'm able to just barely drive that thing about all the way up before the inverter craps out. All right. Just barely see it show up on the scope here with the probes just all the way over here. Bring it back. So yeah, if I hold just the probes out here, you know, you pick up that voltage, about 160 some kilohertz, and I'd say it runs that bulb better. And there's no arcing all over it, which obviously is a bonus there.